Okay. Hello, everyone. So this is a continuation after the installation video, which was the previous one. This one is going to step through several things, some of which we went through on Friday, some of which we did not. I will be going kind of quickly through this. But that's okay, because this is a video. You can always pause it, go back in time, follow along. To aid in that, you'll also notice there's this yellow circle behind my cursor, and when I click, there will be a red dot to tell you that I clicked. Hopefully that'll help you follow along a little bit better. Um, that said, let's go ahead and jump into this. So, we will want to be modeling a fairly basic shape. We just want to model a cylinder, let's say. So, if we want to model a cylinder and we want to know what does the flow field around a cylinder look like, well, we probably, if you're taking this class, have a pretty solid idea of generally what the flow field around a cylinder looks like. But we want to test that understanding and try and simulate it and see how that works. So, to that end, we're going to need to create a model of a cylinder. We have a couple of ways we could do this. We could import a surface mesh that defines the exterior of our cylinder. We could import a three-dimensional model or a CAD model that represents a cylinder or that represents the air around the cylinder, as you'll see is important in a minute. However, a cylinder is really, really simple. We don't need to do anything fancy and import it from external libraries or external sources. We can make this directly in STAR-CCM+. We have a couple ways to do this. We could do this by making a new 3D CAD model. There we go. Where we have some basic modeling tools and a three-dimensional workspace to play around in. We can select planes, we can make sketches similar to SolidWorks or most other modeling software, as well as basic extrude type commands. So let's, just as a really, really quick example, I'll go through a couple of these. So let's start on the XY plane, and we're going to create a sketch. Well, we have a couple things. We can make points, we can make lines, we can make rectangles, we can make 3-point rectangles, we can make circles, arcs, other types of arcs, ellipses, or splines. Please don't try and make a spline. It's just going to give you a headache for the most part. We could drop a circle there and click OK. We have a sketch. It's a circle on the XY plane. We could right-click on this sketch on the left here and extrude and make a cylinder because it's a circle extruded in one direction. You could change how far you want it extruded. You could switch the direction you want it extruded. Let's see, -1. You could draft it in or out. You could do all kinds of fun stuff with extrudes. We are going to do none of this. This is one way you can make the cylinder. This is one way you can make complex geometries, much the way you would use any 3D CAD software. This can be very powerful depending on what you are doing. We will save some of the more powerful features and discuss this later. For now, we're not going to use it. I'm going to delete that. We don't need it. If you're making basic geometry, blocks, cylinders, cones, spheres, etc., we don't need to use the 3D CAD model. Instead, we can look at this subfolder, so geometry, parts. If we right-click on parts, we have a couple of options here. But the important one at the moment is new shape part, where we can make blocks, cones, cylinders, and spheres. We are going to make a cylinder. We can change the dimensions pretty freely if we want to. You can a cylinder is basically a line or a circle that is extruded along a line. a line that exists in three-dimensional space, and perpendicular to that line, you would extrude a circle. So if you start the line at a point, you end the line at a point, and you tell it how big the circle is, you've fully defined a cylinder in three-dimensional space. Pretty useful. The defaults are, it starts at 0, 0, 0, 3 XYZ coordinates, and it has a radius of 1 meter. That's a pretty big cylinder. We're going to turn down the radius. And the end coordinates are at 0, 0, XY, 1 meter in Z. That's probably okay, but we're going to make the radius smaller. So we're going to make the radius something like 1.5 inches, give or take. We're not too picky about what the radius is, but we're going to make it 40 millimeters. We could get fancy and use other coordinate systems. We can tell it we don't care how accurately this represents a cylinder, or we could tell it that we very much care how accurately it represents a cylinder. But in practice, the tessellation density, medium is usually okay. It's pretty intelligent about how many facets, how many features it uses to make up shapes. So we're going to leave the laboratory system or the coordinate system as laboratory, because it's the only coordinate system we have currently. We will talk more about coordinate systems later. Tessellation density, we have options. We are going to leave it as medium. If you wanted to see some more information about this, you could click help, and it will pull up the help documentation. Generally, hopefully, about the right thing. And this tells us how you could go about making a part and how the parts are defined. But this is okay. So we're going to start with 0, 0, 0 for our start coordinate, 40 millimeters for our radius, and 0, 0, 1 meter for our end coordinate. And click OK. Geometry, under parts, it has created a cylinder. Now we can't see anything yet, and we need to fix that because we want to be able to see what does our cylinder look like in three-dimensional space. If we want to see anything that is spatially relevant to our simulation, we need to move outside of this geometry folder. This geometry folder is not what we want. Instead, we are going to want our scenes folder. Scenes, by and large, are going to have to do with anything that has to do with three-dimensional space or two-dimensional space as it is implemented in our simulation. Specifically, we want to see what does our geometry look like. What does our cylinder look like that we just made? We can visualize things in many, 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 many different ways. But for now, we just want to look at what does the geometry look like. We could hypothetically look at what the mesh looks like if we had a mesh yet. We could hypothetically look at any scalar quantity. Pressure, temperature, density, etc. We could hypothetically look at any vector quantity, velocity being the big one. Or we could look at nothing at all if we wanted to create an empty scene. For the moment, we want to look at the geometry. So we're going to create a new geometry scene. Well, we have our little coordinate system in the bottom left here to tell us what direction we're looking from. And we have our cylinder. We can select it in the viewer and see. Hey, that's definitely our cylinder. It's far smaller in diameter than it is in length, which was intended. It's a meter long, but only 40 millimeters in radius. So that is definitely our cylinder. Okay. But while this is absolutely a cylinder, this isn't actually what we want to model. We don't care about the cylinder itself so much as we care about what the flow around the cylinder looks like. So we need to define a volume that is the air around the cylinder and not the cylinder itself. Right now we have our cylinder, which is a good starting point. But let's create a block to represent the air that is nearby the cylinder. And we'll use that to represent the air that is around the cylinder. So, same thing, except we're not making same thing as making the cylinder, excuse me, except we're not making a cylinder anymore. We want to make a block. And because we actually have a scene open this time, we see we have some more options to make this block than we had for the cylinder. We can input coordinates just like we did before. Very useful. But we can also drag these handles around. We can drag the edges to move each face. We can drag the centroid to move the entire thing. We can do all kinds of fun stuff. We could tell it to snap to a given part and basically say, hey, make this the size of our cylinder. That's absolutely possible, and I just did that again. I don't want it to be the same size as the cylinder, though. So we're going to uncheck that. Now, how big do we want this block to be? Well, we want it to be the size of our cylinder as far as width goes in the Z direction. That's fine. I didn't mention it previously, but I fully intend on this being a two-dimensional simulation for computational cost reasons. So we're going to... Having the Z as 0 and 1 is perfectly all right. That's excellent. But we're going to need some volume of air around this thing. And what we're going to have, and we kind of need to think about this a little bit now, is what direction do we want the air to be coming from? If the air is coming from the left, well, we don't need all that much distance in front of the cylinder. We need some, certainly, but not a huge amount. But if you know anything about flow around cylinders, you know this thing's going to leave a wake. Probably a pretty considerable one. So we're going to need a lot more distance behind this thing before we reach their boundary. Because in general, the ideal state of affairs is your boundaries are far enough away from your object of interest, in this case our cylinder, that the flow from your object of interest won't meaningfully affect anything that's going on at the boundaries, except maybe at the back, and only a little bit. So we're going to leave a little bit of space in front of this thing. We're going to leave, let's say, 1 meter in front of this, approximately 1 meter. And we're going to leave 2.5 meters behind. This is relatively simple because we know that this cylinder is located at 0, 0, 0 on one end and 0, 0, 1 at the other end. So we can just say, okay, we go negative x, 1 meter, and that puts us a little bit less than a meter in front of the cylinder. We can go 2.5 meters in the positive x direction, and that puts us pretty considerably behind our cylinder. And if we want the cylinder centered vertically in this space, we can give it, let's say, -1 and +1 meters. So there's about a meter above and below the cylinder. About a meter in front of it and 2.5 meters behind it. And this block goes from z equals 0 to z equals 1. This will represent the volume of air that is around the cylinder. And actually in the cylinder too, because there's no special condition that says this block doesn't exist where the cylinder exists. If we hit create, as a matter of fact, we can highlight this block and see that, yep, that block goes right through our cylinder. It's not doing anything to prevent those two overlapping. Which is fine for the moment. But clearly, if we have a physical cylinder there, air is not able to pass through it. So what we need to do is say, no, 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 no. We have the air around the cylinder, but it can't go through the cylinder, right? So what we need to do is we need to remove the cylinder from the air around it, from this block that we just made. This goes for pretty much anything you're modeling, right? As long as it's a solid thing, air is not going to be occupying the same space as the thing. So whether you're modeling an aircraft, a boat, what have you, you're never going to have any fluid that occupies the same physical space as the object. There's some minor exceptions if you're modeling something like a heat exchanger. But in general, you're always going to want to remove the object from the volume of fluid nearby so that you have a void or a hollow inside of the flow that represents those boundaries where the flow hits the object and has to go around. But how do we go about removing this volume that is our cylinder from our block? So we can make things under parts. We can change their shape. And actually, if we click on these things, we can see under properties, we can change the properties of these things. I can make this cylinder 80 millimeters. I can make it 40 again. I can make it 3 inches in diameter. I can make it 1.5 inches in diameter. I can make it 1 foot in diameter. Or radius, excuse me. I can do many different things. I'm going to put it back to 40 millimeters. I could change the endpoint. I could say, nope, we want this to go to 3 meters. Make it longer. I can say I want it to be shorter. It's going to go to 0.5 meters. You can change all the properties about the thing down here. But you can't remove the cylinder from the block with any of these properties. You can change things about the thing itself, but this doesn't affect how the thing interacts with anything else. For that, we need this folder called Operations. Operations involve several different things, including cleaning up surfaces, doing preparation, stuff like that. We could hypothetically move or rotate this cylinder in three-dimensional space. As a matter of fact, we might be able to just extract a volume. Let's see what this did. Okay, never mind. That was just a point of personal curiosity. Don't mind me. What we want to do is remove the cylinder from the block. So that would be under Boolean. This is basically saying, can we add things? Can we combine things? Can we subtract one thing from another? Plus a couple of other options involving making faces that are touching each other separate and stuff like that. So what we're going to do, actually, is subtract, because we want to remove the cylinder from that block. So we create a subtract operation, and each operation is going to have different inputs. It's going to have different controls to some degree. But they'll all probably use a dialog that looks vaguely like this. So input parts is everything involved in the operation. For a subtract, the target part is the thing that you want to subtract stuff from. And then if any of this was on the 3D CAD folder up here, you probably want to check that. We don't need it because we don't have anything there. And if you want this to do this operation right away when you click OK, you would check that box. I'm going to leave that checked. If you want to read more about this, you can go to the help documentation, operations, executing operations. Performing Boolean operations. And you can read more about Boolean mode and uniting, intersecting, subtracting, etc. Imprinting. You can read more about it there. But in any case, let me get that out of the way. We want to subtract our cylinder from our block. So we need to select both our cylinder and our block. And we want to select the thing that we're subtracting volume from. Since we're removing material from the block, we select the block. And we can click OK. And because we checked that box, execute on creation, it already did this. And now we have a new part called subtract, which has a hole in it that is the same size as our cylinder. We have successfully removed our cylinder from our block. We still have our cylinder and a block, but it created a new part that is the result of this subtract operation. We could change the size of our cylinder. We still can, even though we've already subtracted it. But notice that a little exclamation mark shows up next to these things. This exclamation mark is just saying, hey, I did a thing, but then you changed the stuff that I used to do it. Your thing is out of date and needs to be updated to be accurate. Happens all the time. So what we can do here is we can right-click and hit update on either one of these things. Or sorry, we can right-click on the subtract thing and hit update. And you saw it made that cylinder a little bit bigger. And it changed it. It reran the operation, and it took a look at that cylinder, took a look at that block, and said, hey, let's do this again. It did it again, and it changed the result. So I'm going to just put it back to 40 millimeters here. I made the cylinder 60 before. We updated it. I made the cylinder back to 40 millimeters radius. We can also tell it to execute an operation. And it'll do the same thing. It updated it. It reran the operation. The hole in our block is the right size again. Now, if we look at our block, we notice, or if we look at our subtract for a second here, it is going to kind of inherit all the surfaces from the things that were making it up. We can see it inherited a cylindrical face from our cylinder. We can see that it inherited a whole bunch of flat planar faces from our block. But these surfaces are just one piece. They're definitely discrete surfaces, right? They're all 90 degrees to each other. But this shows it as just one surface. Sometimes that's fine. But sometimes you need more individual control over surfaces. So if, for example, we want the flow to be coming from the left here, we need to specify that the flow on this front face is, well, it's entering this block. We need to specify the flow outlet over here on the right. We need to specify what is the flow doing, what are the boundary conditions on the top and the bottom, and the boundary conditions on the cylindrical face, but we already have our cylindrical face, so that's not an issue. But we need this block to be multiple pieces. How do we go about breaking up a block into multiple pieces so we can actually use it? Or we can actually use each of these faces individually. We have a couple of options, but they all involve right-clicking on this surface. So we see we have under geometry, under parts, we have our block. Under our block, we have surfaces. Under our surfaces, we have one surface. If we right-click on this surface, we have a couple of options to split it up. as well as some other options that are a little bit more complicated. So we have a couple of options that are immediately relevant, and these three in the middle are not immediately relevant right now. This is a block, so we know that all of these faces are 90 degrees to each other. So we could split by angle. And if we split by 89 degrees, that will give us 6 faces. We could definitely do that. That would actually be a very efficient way of doing what we're about to do. But I would like to take this opportunity to introduce you to a second very useful way to split surfaces, which is split by patch. This is a manual process, but can be very powerful because you get a lot of flexibility in how you select things. If we say split by patch, and note you have to have some kind of geometry scene or some three-dimensional scene open to split by patch, you'll get some options here. It will list the different numbered faces of your part. It will color all the faces a different color. Notice one of them is pretty close to the purple that it uses to highlight these surfaces, which is a little bit inconvenient. It's always going to look like this top face is selected, even when it's not. That's just annoying. It's not actually selected. But we can select any of these surfaces. Like, let me select the part that is upstream of our cylinder. It's a little bit hard to see, but our cylinder is right here. So if we select the part that is upstream of our cylinder, we can see that that is face number 57. It is selected. The side wall is face 55, the top wall is face 58, the bottom is face 56, etc. But we can say, okay, let's take face 57. And we want to name it inlet. So we know that this is the inlet. And if we select it, we name it inlet and hit create, it will remove that face and it will create a new surface called inlet. It's no longer part of this list. That's expected. We also can take the opposite face, this green one back here, and say outlet. Create. I can select this top face, face 58, and say top. I can select this bottom face here and say bottom. You can even select multiple faces at a time and do this with several. As a matter of fact, usually you're dealing with several faces at a time. It's the same process, you just control click and select multiples. You name them, it works fine. However, what it won't let you do is take the last face. There always must be one surface remaining here. It won't let you remove the last one. A little bit inconvenient, but that is a limitation of the split by patch tool. Doesn't really matter. Let's go ahead and... so this is going to be... I'm going to call it plain. It'll be obvious why in a little while. We can't actually rename this last face. I can type in whatever I want here. It won't let me create anymore. But that's okay. We can take this and rename it just by double clicking. And I'm going to call this out of plane. So what we just went through was we took the one surface that used to represent all 6 faces of our block and we split it. So they are now each independent surfaces. You can also flip through this list just with your arrow keys if you'd like I'm doing now. So we have our inlet, we have our outlet, we have our bottom, we have our top, we have our plane, we have our out of plane. Notice the subtract needs updating again. Well, we changed the block, right? Instead, we changed it in the sense that we took it from one surface and we made it 6 surfaces. It's still physically the same shape, it's still physically the same size, but because we changed something about it, it needs updating. If we look under the subtract, we can see that this thinks it still only has 1. So we're going to go ahead and execute the subtract again. If we look at this, we can see that this now has 6 surfaces. It has a top, it has an outlet, it has a plane, outer plane, inlet, bottom, etc. So once we reran our subtract operation, this inherited the changes from our block, which is good. We have our subtract, we have our hole that represents our cylinder. This represents our domain. This represents what volume we will be simulating. Now, what are we simulating? Well, this is our geometry, all right? But we need to go through and look at our physics. What sort of phenomena are we simulating? That doesn't take place in the geometry folder. That takes place in the continua folder. We did not get to this in class. This is an extension from what we discussed in class. We will go over this somewhat in class this coming Friday. But we are going to define the physics that we are going to use. So we can right-click on Continua and say New Physics Continuum. You can have more than one of these. However, for the moment, we just need one. I'll get into what multiples of these can be used for later. And to tell it what physics we actually want to use, we select our physics continuum, right-click, and say Select Models. This is where we select the physics models we want to use. So, what do we want to use? Well, we have a couple of choices here. We can use an axisymmetric model, where it pretends the body is radially symmetric. We could do a 3-dimensional shell. We could do 3 dimensions, or we could do 2 dimensions. If we're modeling a cylinder, 2-dimensional is probably what we want, because an infinite cylinder is going to be a 2-dimensional flow, right? If you have a cylinder that's, let's say, looks like that in a shape, then it's not going to change. Anywhere along the length of that is going to look exactly the same. So this is going to be a 2-dimensional problem. And you can look into why exactly that is and think about that, and we can maybe discuss a little bit in class. Now, the question is, do we want to just model this cylinder as if it was the flow around the cylinder had existed for an eternity? Or do we care about how is the flow field changing with time? Well, it's a cylinder, so if you know much about aerodynamics, you do know that it is going to be changing with time, right? This is going to be unstable. It's going to have flow properties behind the cylinder that absolutely do change with time. But just because something changes with time doesn't necessarily mean we care about those changes with time. You could still absolutely do a steady state, a steady simulation with something that is inherently unsteady. It might be a little bit harder to get it to converge, but you can still do it, and it'll give you something akin to kind of what does the average flow field around this thing look like? What is the average velocity at any given point? Sort of. This is a slightly more advanced topic. We will get to it a little bit later. Right now, just to impart the basics, we're going to select a steady simulation. Now, are we dealing with a gas? Are we dealing with a liquid? Are we dealing with a solid? Are we dealing with a multi-component gas? Maybe it's a mixture of gases. Helium, hydrogen, argon, krypton, xenon, carbon dioxide, oxygen. Take your pick, right? You can have mixtures of gases, right? Luckily, for our purposes, air is considered a single component gas. While it's principally made up of nitrogen, oxygen, and some other stuff, and carbon dioxide plus some other stuff, it's considered, for all intents and purposes in the simulation software, one gas. We could absolutely just do this with air. We could also do it with water, which would be a liquid. However, we are going to stick with air for the moment. This is this is aerospace engineering class, not a hydro engineering class. So we're going to stick with air for the moment and select gas. Now, this next choice isn't going to make a lot of sense unless you understand a little bit about how the Navier-Stokes equations work and how solvers work a little bit conceptually. This will be touched on in class, but at the high level, there are 5 equations that govern fluid mechanics and how they behave. These are referred to as the Navier-Stokes equations. You have one equation that involves mass. Where is mass entering? Where is mass leaving? What is density increasing? Basically, is it accounting for where all the mass in the system is going? You have one equation for that. You have one equation that describes momentum. How fast and how much flow is going where? Momentum in the x direction specifically is the second equation. Then you have momentum in the y direction, you have momentum in the z direction, and last you have another equation for energy. Where is energy coming from? Where is energy going? How does it interact with the flow properties? Things like that. Coupled flow is going to solve all of these equations simultaneously. It's going to build, no matter what you do, it's going to build basically a system of linear equations that it solves. An immense amount of matrix math. With coupled flow, those quantities are going to be interdependent. Right? It's going to solve all 5 of these equations simultaneously. With segregated flow, it's solving continuity. And then it says, okay, I'm done solving continuity now. I'm going to go solve momentum. Okay, I'm done solving momentum. I'm going to go solve energy. It bundles and separates and segregates these equations as it solves them. Now, what does this mean in practical terms? In practical terms, it means that if you have flow qualities that are highly interdependent, like if you have a lot of energy going on in the flow, you might need to use coupled flow because energy is going to affect momentum, energy is going to affect mass, etc. Things like transonic or supersonic flows, or hypersonic flows, or flows where you're dumping large amounts of heat into the flow can require coupled flow solvers. Subsonic flows that don't have a very large dependence with energy, basically, if you're dealing with something that's pretty much incompressible or like probably less than half the speed of sound, maybe even up to like Mach 0.8, 0.9. If it's a very clean aerodynamic supersonic body, maybe even slightly above supersonic, you can use a segregated flow solver. It's slightly faster and behaves differently in several other ways. But again, it solves these equations separately, so it's slightly less accurate in any one step. For now, we're going to be dealing with a low velocity cylinder. So we're going to select segregated flow as I have just done. Now, we told it that we're dealing with a gas. Okay. We told it that we're dealing with a segregated flow. This is two-dimensional. This is steady. Notice it added an extra gradients term in here. That is required. You don't get a choice in the matter. So it added it automatically because it was just required to use the segregated flow solver. But now we need to define, we need to tell it, okay, how does this gas behave? Is it just going to be constant density? Is it going to behave like an ideal gas? Is the density going to be some polynomial equation? Oops, excuse me. Is it going to behave like a real gas? Or is it going to follow some other equation that you can define? User-defined equation of state. In practice, what we're dealing with is probably going to be constant density. Again, low velocity flow around a cylinder. But even the slowest flows are going to change in density slightly if they accelerate or decelerate at all. If their pressure's changing, the density is going to change a little bit. Maybe not enough to actually affect anything. But we're going to go ahead and select ideal gas to attempt to model that. And now we have a couple of options here. We told it that it's an ideal gas, right? So it knows that density, pressure, temperature are interdependent, right? How are they going to interact with each other? Well, think on that for a second, and I need to go check something. I will be right back in just a moment. Okay, sorry for the delay. Hopefully you've thought of what these mean a little bit. It's basically asking for how should it treat the fluid when it's referring to that energy equation. Should it treat the fluid as the same temperature all the time? Isothermal, right? Same temperature. Should it allow temperature to vary? Specifically, like how does it implement the equations? Is it based on temperature? Is it based on enthalpy? Is it assuming the flow is isothermal? How do we want to deal with the flow? In practice, this case probably is not going to matter a whole lot. Again, the flow is effectively incompressible. Temperature is really not going to change substantially. It might get a small temperature change in the boundary layer on the cylinder, just due to viscous heating. It's not going to matter very much for the overall scenario, though. But if you really, really cared about small temperature changes, you absolutely want to model it somehow. In this particular case, we're just not very concerned about it. Again, I skipped it, but step one is, what is the question you're trying to ask? What do you want to know? In this case, the answer is we're trying to learn how to use the software. We're not trying to know too much about this flow scenario in general. So segregated fluid temperature is usually my go-to. We're going to go ahead and use that. Now we need to know, okay, how is viscosity in this flow going to behave? Is it laminar? Is it turbulent? Is it inviscid? Does the flow have any viscosity at all? Well, the answer is it does have some viscosity. It's definitely going to have some velocity. And is the flow around a sphere going to be laminar or turbulent? Probably turbulent, right? If you know, again, much about aerodynamics at all, a relatively blunt shape like a sphere is going to have a very turbulent wake, or cylinder is going to have a very turbulent wake behind it. If you were dealing with something nice and clean like an airfoil that you expected to be fully laminar and was going slow enough, or had a low enough Reynolds number that you expect it to be completely laminar, you absolutely could select laminar here. If hypothetically you had a case where viscosity didn't matter at all, you could select inviscid, or mattered not enough to really matter. You could select inviscid. Because we're dealing with a relatively blunt body, we know it is going to have a turbulent wake. We are going to select turbulent. We have a couple of different ways that we could potentially model turbulence. These ways get increasing, or actually, this way is, I think, one of the simpler ones, now that I think about it. But we have several different ways we can model turbulence. These are all going to be different. These all change what equations it uses to model turbulence. Okay. Now, the exact way it models it isn't going to be stupendously important here. But let me go over some general rules of thumb for the different applications for a couple of these. I'm going to start at the bottom. The Spolart-Almar's turbulence model is generally well suited to clean aerodynamic shapes where you expect the flow to be following the surface the entire time. You don't expect flow separation. Things like airfoils, for example. It'd be pretty well suited for that. It does not deal with separation well. It will very likely not work very well for something like a sphere, where you know that the flow is going to leave the surface of the sphere. It's not going to smoothly follow the sphere, or the cylinder, excuse me, around the entire surface. Going back to the top, K-epsilon turbulence. It's a way of modeling turbulence that involves turbulent kinetic energy and other quantities represented by the epsilon. I forget exactly what it is. But it's using two equations. Spolart-Almar's uses one equation. So K-epsilon turbulence is a little bit more computationally expensive. But it is potentially, depending on scenario, somewhat more accurate. K-epsilon turbulence will deal perfectly well with flow separation under most scenarios. But it does have an issue. if flow separation does occur, then K epsilon won't necessarily do a very good job of predicting where it occurs. It will predict that it happens, but it won't necessarily accurately predict where it happens. So for something like an airfoil at or near stall, where you expect flow separation, but where the flow separates is important, it's probably not the best choice. If you had something like a box and you knew flow was going to separate instead of turn that corner, it was just going to go up, it'd probably be a perfectly reasonable choice for something like that. K omega is a different two equation way of modeling turbulence. It is more well suited to predicting where flow separation occurs. K omega, as I've heard it in multiple different venues, is usually kind of the go-to turbulence model for aerospace applications where flow separation is expected to occur. Things like airfoils at high angles of attack, for example. Or many other applications within aerospace. I'm just oversimplifying to some extent. But if you expect flow separation, and you need to know where it occurs with a fair degree of accuracy, K omega turbulence is probably better. Reynolds stress turbulence is more accurate still and has to do with a whole bunch of extra terms that it will incorporate, but is significantly more computationally expensive. Which one of these you choose, you'll probably not choose Reynolds stress turbulence very often in my experience. But the other three depends on the scenario, right? Because we're dealing with a sphere and we don't know exactly where it's going to separate, we're going to go with K omega. Because we might be interested in where the separation occurs. So you'll note that both of these things up here now say optional. Right? This is a different way of predicting the transition point between laminar and turbulent and things like that. I'm not going to select it for this one. We can go into some more detail about that. If you want to hear more about these various models, you can always click on help and read the documentation. This will be a very, very, very deep dive if you choose to start looking into stuff like this. Just so you're aware, you can, absolutely. And to some degree, I do recommend looking into the things you intend to use, just so you understand how they work. Just be careful not to get lost and accidentally jump into the stuff that you're not going to use. Because that could get... actually, as a matter of fact, we're not using that. Simulating physics, viscous flows. It tells you about some of the ways it models viscous flows. Etc. You can flip through this and take a look at the various things. Again, this is a lot of documentation on many, 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 many different topics. You could literally read this for days or weeks or months and probably not know all there was to know about it. We're not going to be using that model, any of those models this time. There's other optional models. If you expect cell quality to be a problem, you can turn this on. If you need to turn this on, something has probably gone wrong. If you're dealing with electrochemistry, there's an option for that. Electromagnetism, there's an option for that. Gravity. Oh, gravity is a thing. Let's go ahead and turn that on. If you're dealing with multi-phase fluids, there's a way of modeling that with Lagrangian mathematics and other interesting things. You could select that if you're dealing with something like that. Mesh deformation. If your mesh is going to be changing as the simulation progresses, you need to select that. Porous media, if you're dealing with something like a particle bed reactor or something like that. That might be useful. If you're dealing with radiation, thermal radiation, whether it's gray thermal or spectra dependent, radiation will let you model the interaction of electromagnetic radiation with your scenario. Thermal comfort, if you're dealing with crew cabins and people need to be comfortable or at least survivable, thermal comfort can give you extra options to deal with that. If you're dealing with thin films, whether you're dealing with vorticity confinement, stuff like that. These will generally rarely be used, but if they are, they will be specifically relevant to your scenario. If they're not specifically relevant to your scenario and you're using them, something's probably gone wrong. Gravity is kind of an exception to this. It's sort of a catch-all. If you have flow where you expect gravity to matter, like if you had a natural convection flow, for example, with like a heated plate and hot flow rising, cold air coming in underneath, the only reason it rises is because of gravity. You would need gravity to model something like that. But those are our physics. Rename. Air. If you select gas as a model, we selected gas, it's going to default to air. If you select liquid, it's probably going to default to water with the thermal or with all the properties that are associated with those. And you can, if you wish, edit them down here. These are just all constant values. That is fine for this application. But remember, if you're dealing with things other than air, you will need to go in here and tell it to change what you're dealing with. There are many gases in the library, or you could make your own. There's a couple of extra options. Generally, the defaults are fine unless you're dealing with fairly specific other applications. Ooh, I forgot about that. Unless you're dealing with specific other applications. So, if you're dealing with like hypersonics, some of these more advanced parameters might need tweaking. For more subsonic stuff, it's fine. Reference values, it'll be asking you things like, which direction is gravity going? I'm actually going to tell it in the negative y direction. So, oh, no, sorry, it defaulted to negative y. It says 0, negative 9.81. So this is, gravity is in the negative y direction. It's just fine. Reference altitude. Well, air pressure goes up or down depending what altitude you're at, right? So this is just saying that, hey, just my reference altitude, what I'm considering 0, is at what height. In this case, just 0 meters. It's fine. We're at sea level. There's some meshing parameters. If pressure, or if there's ever a cell that is closer to a wall than this, what is that, like 1 micrometer? It's going to make it 1 micrometer away from the wall. If it ever gets a pressure that is higher than 1 times 10 to the 8th pascals, it's going to set the pressure to 1 times 10 to the 8th instead. That is the maximum pressure it will allow. The reference density. What is it expecting the density to be? Well, the answer is it's probably not straight up 1. It's probably closer to 1.18 for most applications. I think at about 23 degrees Celsius, it's going to be 1.18. Reference pressure. What does... Okay, let me back up a second here. Minimum allowable temperature. What is the minimum temperature it'll let it be? If it gets to anything below 100 Kelvin, it is going to set the temperature to 100 Kelvin at that spot. Ditto pressure. If it gets to anything less than 1,000 pascals, absolute pressure, it is going to set the pressure to 1,000 pascals at that spot. Maximum allowable temperature. If it gets to 5,000 Kelvin anywhere, it's going to say, nope, this is too hot for me. Put it back at 5,000. At that location. Reference pressure is slightly different. unless it specifically says absolute in front of it, all of the pressures are going to be, all of the static pressures are going to be relative to this reference pressure. If it says 0 pascal static pressure, it doesn't mean the pressure is 0. You are not in space today. What it means is the pressure is exactly the same as the reference pressure. If it says your static pressure is 1,000 pascals, it means your static pressure is actually whatever this value says plus 1,000. Or minus 1,000, or whatever else the number says. You can also tell it, in addition to the models themselves and these reference values, you need to tell it, okay, how does the simulation start? Is the pressure above or below 0? What is the temperature of the simulation? What is the turbulence like? How intense is the turbulence in the flow field? How is it going to figure that out? The answer is, for the turbulence, the defaults are probably fine. What is the velocity of the flow? Well, the answer is the velocity is probably something. We're going to start it at 20 meters per second is about 40 miles per hour. We're going to start it at 15 meters per second. So 15 space 0 meters per second. So that will be flow moving in the positive x direction at 15 meters per second. And when we start the simulation, when you hit this little green flag, or tell it to run or do whatever, it's going to say, hey, I'm making the velocity everywhere, irrespective of where it is, because this is constant. 15 meters per second. So, those are our physics. Now, we're going to briefly go through some meshing really quick here. I think we're going to probably have to stop after that because I'm about to need to head off for my other class, but we'll see how this goes. So, when we mesh things, it's done, at least there's a couple different ways to do this. The way that is going to be supported into the future is with mesh operations. So there's surface preparation if we wanted to clean up or do stuff with our surface. We don't. This is pretty self-explanatory. Or we've already have a very clean surface. We just have a cylinder and a block. Nothing fancy. There's nothing to clean up. There's nothing to prepare. We already did our Boolean stuff, but we do need to mesh this. Now, I mentioned we're doing a two-dimensional mesh. When we do a two-dimensional mesh, you need to tell it, or you need to make it basically figure out, okay, what plane are we using? Because right now, we have a three-dimensional block, right? What is it actually simulating? Is it simulating, let's see here. Is it simulating that plane? Probably not. It doesn't touch the cylinder at all, right? Are we simulating the inlet, that plane? Probably not. Also doesn't touch the cylinder, right? Are we simulating that plane? Well, we could be. That definitely looks like it could be a, flow coming this way, move around the cylinder, flow out that way. This could be our simulation. Or it could be that plane. Same thing. Flow come in, flow move around cylinder, move downstream. It basically has to pick some two-dimensional plane to simulate. So the way you get it to do that is you create a new operation, so geometry operations, new, mesh, badge for 2D meshing. And you tell it, we are going to mesh the the subtract, because this is the thing that is the air that has the cylinder removed from it. Now, you actually don't get any control over which plane it looks for. When you badge a thing for 2D meshing, it expects to find a plane at z equals 0. It is looking for a surface at z equals 0 that is parallel to the xy plane. That is why we left this block the way we did. Where we left one corner of it at z equals 0 and the other at z equals 1. That's why we left our cylinder starting at z equals 0 and ending at z equals 1. So there would be a face, specifically what we call the plane, that exists at z equals 0. And when we badge for 2D meshing, it goes and it finds that. And it did indeed find it because it didn't throw an error. Hypothetically, let's just make this 0.25, let's say. I can rerun the subtract, and I can tell it to execute this, and did it figure it out? Well, the answer is no, it didn't, because you notice, if you look closely, there's no little red dot here. Whereas if I put this to 0 again, and I run the subtract, and I run the badge, look closely at this subtract up here. Execute. It has a little red dot. This tells us that it has actually been badged for 2D meshing. And you'll notice these things look different. What this is saying, what these little symbols are saying, is that this is an edge. This is one of the edges of our domain. This bottom surface is, instead of in 3 dimensions a surface, it's a line for us. Inlet, same thing, it's a line. Outlet, same thing, it's a line. Out of plane, it's this gray symbol. It's not even involved in this simulation at all. Plane, well, this is actually what we're simulating. You see the little red dot? And how it's a solid red? This is how it's telling us which 2-dimensional surface is it actually simulating. And then top is just a line. If you're dealing with 3-dimensional stuff, it doesn't do this. You do not do this if you're dealing with a 3-dimensional simulation. You do this still for a axisymmetric simulation. But you don't do it for a 3-dimensional simulation. Again, it went and it found the surface that existed at z equals 0, parallel to the xy plane. It found it, and it turned that into our simulation domain. Instead of the entire block, it's just that one 2-dimensional surface. Now, we need to actually create a 2-dimensional mesh. Well, there's an automated mesh 2D. That's probably what we want. As a matter of fact, that is what we want. And we want to mesh this subtract. Again, notice the red dot. That tells us it has been badged for 2D meshing. Now we have a couple different options here. We could mesh it with polygons. We could mesh it with rectangles. Or we could mesh it with triangles. In my experience, in 2-dimensional meshes, the polygon works pretty well. Quadrilateral does some weird stuff in 2 dimensions. Triangular, well, triangles aren't great for meshing in general. The reason is just because there's so few faces that they exchange properties with adjacent triangles poorly. Polygon is probably what we want here. And if you care about boundary layers at all, you are going to want to select Prism Layer Mesher. That is important. I'll explain what the prism layer is in a minute, but it's probably faster to just show you and then explain it. So, you'll notice there is a new operation, Automated Mesh 2D. Well, we told it that we were using a polygonal mesher, that's fine. We told it that we are using a prism layer mesher, so it added those two. That's fine. That's exactly what we wanted. There are some options here. These tend to be best left as default unless you're trying to do something very specific. Where the rubber will meet the road is these last two folders, default controls and custom controls. Default controls are what it uses for everything in this mesh unless you tell it to do something else. So, the base size is this does nothing by itself. This is a reference number. So 1 meter is a reference size. If you had a CAD projection, like if you had anything available on the 3D CAD level, what this would do is it tries to make sure the surfaces match that CAD as closely as possible. Generally, leaving that checked is probably a good idea. The default is fine for most applications. Target surface size is the first one of these that really matters. How big is it going to try and make each of these polygons? Relative to that reference base size that we set a second ago. Now remember, this entire domain, this entire subtract, is only a meter in this direction and 2.5 meters this way. But the default 1 meter that it's trying to set is probably going to be way too big. Way too big. Let's make it something more like 5 centimeters. 2 inches. Still not small. 2 inches, about that big, give or take. Still not small, but a lot smaller than 1 meter, right? So now our base size will be 100%, or sorry, it will try and make everything as large as it can up to 100% of that base size, which is 5 centimeters. This is something we will need to go through in class, I understand, but I just want to try and get people familiar with it for the moment. Minimum surface size. Well, this is the smallest it will make anything. 10% of that base size. Since our base size is 5 centimeters, 10% of 5 centimeters is going to be 5 millimeters. The smallest it will make any cell is 5 millimeters. We're actually going to turn this down a little bit. No, I take it back. We'll leave it the same. We'll see what type of mesh this generates, and we'll go from there. Surface curvature. Well, any mesh is going to be made up of straight lines. But we're dealing with a circle. Circles are not straight lines, right? So the question is, how many points, how many lines does it take to acceptably approximate a circle? Well, by default, STAR-CCM Plus says 36. If you are modeling a complete circle and you have 36 points, that is an adequate representation of a circle, is what it is saying. Don't bother making the cells any smaller. It will still try and make them the target size. It won't make them any bigger than the target size. No matter what this says, it won't make it any smaller than 5 millimeters. Right? It won't make any cell any bigger than 5 centimeters or any smaller than 5 millimeters. But in between that range, it will add more, or it'll make cells bigger or smaller to try and get at least 36 points in that circle. Surface proximity. This one's a little bit more complicated and hard to explain here, but if you had 2 cylinders that were very close together, it would try and get a minimum of 2 cells in between. is what this is saying. It would try and get 2 cells in between those 2 adjacent cylinders if you had another one right here. Or you could turn this up and get like minimum of 6 cells in between. Or however many you want. If you turn this number up too high, you're going to have more cells than you need, but you absolutely could turn that up as needed. You can also do some things to control where it looks for where cells are close to each other, but we'll get into those on more advanced topics. Next question is, or this next setting is sort of specific to 2-dimensional meshes. But if you have a cell that's, let's say, at the top here, and this cell is 5 millimeters in size, and you have another cell over here that's 5 centimeters in size, well, how does it transition from one cell size to another? I mean, it has to get bigger, right? But it doesn't make it bigger all at once. It makes it bigger gradually, right? It gets slightly bigger, slightly bigger, slightly bigger until eventually it reaches its maximum size. Potentially over here or potentially even here. The surface growth rate is just saying that the size of any 2 adjacent cells is not going to change by more than a factor of 1.3. At most, a cell is going to be 30% bigger or smaller than the adjacent cell, is what this says. Well, actually, technically, fast, default, or slow, but if we want to specify a value, we can tell it 30%. Has to be at least a value of 1. Maximum is infinity. It tells you the available range right there. We will leave this as default. Note, because it is default, it is not actually 30%. It is some system-defined number that isn't immediately apparent. Number of prism layers. I'll explain what this means a little bit more once I can actually point at them. But for now, let's say 8. And prism layer stretching, I will also explain this in a second, but I'm going to say 1.3. And 25. That's probably good enough. We'll take a look and see how this goes in a moment. So these are default controls. It is going to use this no matter where, or sorry, let me rephrase that. It's going to try and use this for everything, unless you tell it to do something else. How do you tell it to do something else? Well, you add a custom control. You can tell it on some curve that you specified. Let's select a random curve. On some curve, you can tell it to do something. You could tell it on some surface to do something. So I'm going to select, not the cylinder surface. I'm going to select the outsides here. So on these surfaces, do something different. Or you could tell it to do something different inside of a volume. Like, hey, inside of this block, which is incidentally the entire domain, do something. What is the something it can do? Well, you tell it. You can change various things. You can change the target size, the minimum size. You could change the surface size in different ways. You could add wake refinement, which is a more advanced topic. We will maybe get to that later. You can change other things for surfaces. You can change surface curvature, proximity, edge proximity, the growth rate, the meshing method, how many prism layers you have. You can also add wake refinement. Again, the help button is your friend. If you don't know what a thing says, open it and look at it. Like, I just clicked help on this target surface size, and hey, look, it tells you what is the base size, what is the basic curvature, what are some of these other things, edge proximity, feature angle, gap closure, minimum proximity, minimum quality, minimum surface size, part priority, blah, 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 other things. And then down here, we probably have, hey, look, target surface size. So use the help menu. It's your friend. This is why the recommended reading is the documentation. There is a lot of it. It is usually quite good. If you see it, use it. Or if you have questions about it, use it. For the moment, I'm only going to leave one of these here. Actually, no, I lied. I'm going to leave two of these here. So what this means, what these two controls means, is on any cell that is touching these four surfaces, so the edges of our domain, because remember, we're dealing with a plane that is in the back here. Change something. So I'm going to change the target size and the minimum size. And I'm going to tell it to not use prism layers. Well, I told it to change it, but what did it change it to? You have to tell it. I mean, I didn't have to tell it a value for prism layers because I just told it to not use them. But for surface size, what should it do instead of using the defaults? Well, I'm going to tell it to use a much larger target surface size, 400% of the base size, and a minimum surface size that's 50% of the base size. So everywhere else, it's going to have its largest cell be 5 centimeters. But on this surface, on these edges out here, its largest size, the target, is going to be 0.2 meters, 400% of the base size. And out, or everywhere, or it'll try everywhere, to make the minimum surface size 5 millimeters. Except on these edges, where we are telling it to have the minimum surface size be 2.5 centimeters. And then I'm also telling it, hey, on this plane that we happen to be simulating, I'm saying that the largest cell you should ever make, no matter where it is, should be 400% of the base size. Nothing can get any larger than that. And let's see what this looks like. Let's tell it to create this mesh. Execute. Oh, oops. Yeah, this was actually intentional. When you have things on the geometry level, you're not necessarily simulating all of them. Very frequently, you're not actually simulating all of them. We don't need to simulate this block. We don't need to simulate the cylinder. We just need to simulate this subtract. And the way we tell it what we're actually simulating is we need to add the thing we're simulating to this regions folder. And this is what this is complaining about. It's saying, hey, you're trying to create a mesh, right? Okay, yeah, we are. But there's nothing that you're trying to simulate. There's nothing under regions. Certainly the thing you're trying to mesh isn't under regions. So what it's saying is, hey, let's go ahead, or what it's telling us is this thing that we're trying to mesh, this subtract, needs to be under here, under regions. Okay, how do we do that? We assign parts to region. Or set new region. I think they both work. But assign parts to region. We'll pull up a dialog that looks like that. It says, hey, what do you want to assign to a region? We can select all of these. We can select just the subtract. We can select none of them, in which case it won't do anything. We want to add our subtract, the thing we are simulating, to a region. A single region. We're trying to simulate one thing. Or we're only moving one thing. So we could also create a region for each part, and it'll create a region called subtract. It doesn't matter too much for this application. However, one thing that will matter is by default, it says create a boundary for each part. We could do this, but it would generate a problem for us pretty rapidly. Because it's going to make one surface, one boundary for each part. So all of our subtract would just be one boundary. That's not what we want. Usually, in my experience, you want a boundary for each part's surface. The curves can remain as default, that's fine. And this last part doesn't really matter for us because this is if you have multiple parts touching each other. How do they interact? Do they not interact at all? Are they physically, like, is one solid, one liquid touching, or are they two liquids touching, or other things like that? Leaving this as default is just fine for most applications. Leaving the curves as default is fine for most applications. But you do want to change this to create a boundary for each part's surface. And generally, as best practice, it doesn't matter this time, but I also create a region for each part. It hasn't created anything yet. It will create this region when we hit apply. So click apply, and if we look under regions, we can see that there's now something there. So we can close this menu, we can open up regions, and we see there's a subtract here that has 5 boundaries, one for the inlet, one for the outlet, one for the top, one for the bottom, and one for our cylinder. Perfect. That's just what we needed. Let's actually tell it to mesh now. Execute. Well, that was fast. It took a grand total of 1/10 of a second. It generated 832 cells. Meshing is normally not that fast. That is very, 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 very fast. It would not be terribly unusual, in my professional experience, to have a mesh take 30 minutes to an hour or more. That would not be unusual at all. For you, that would also probably be a bit slow because we're going to try and keep the meshes on the small side. But in this case, this is probably really fast. We have no idea if this mesh looks okay or not because we haven't seen it yet. If we want to look at the mesh, well, we probably need to actually generate a new scene to look at the mesh. New scene mesh. Aha, we can see a mesh. Yeah, that's really, really coarse. Like, you see these big cells? This is a problem. We expect the flow to be changing a lot more than this around a sphere. Well, good news is we don't have to go through that entire process again. We can just change the base size. Let's make it 2 centimeters instead. And tell it to run again. Better. Let's tell it 5 millimeters. Run it again. It's taking longer. There we go. That's better. Still not great, mind you, but better. Alex, we'll talk more about this in class as far as why you want this to be certain ways. But for the moment, take it on faith that... Oh, actually, no. Actually, don't take it on faith. Let me talk about this for a second. This is a prism layer. It is a layer of cells that are very close to the surface that help model boundary layers, where you have rapid velocity changes near a surface. The velocity is going to change very rapidly, normal to the surface, but probably not change all that much parallel to the surface. So this is designed to capture those large velocity changes due to boundary layers. How thick is your boundary layer? How fast is your flow going? How many layers will you need? Depends on the scenario. This is a prism layer. They are meant to model boundary layers. In practice, this one looks a little bit thin to me. Partially because if you see this size difference between these two cells, that is bad. You do not want this size difference to be that large. So we're going to try that again, and we're going to, instead of telling it 25% thick, we're going to tell it 50%. We're also going to tell it a stretching factor of 1.5. Look at how this distribution of thicknesses changes. Suddenly, they're getting thicker faster, so the top cells are actually thicker now. I'm going to make this a little bit thicker still. We're going to go 75%. Execute. And let's make the surface growth rate slow instead of fast. Let's see what this changes. Aha, see how it got... Their cells are getting larger slightly slower, right? So we went from 800 cells to 22,000 cells. That's still really, really small. That's a small number. Let's crank this up a little bit. Okay, taking a couple seconds. And done. 140,000 cells. Beware exponential growth. I went from a base size of 5 millimeters to a base size of 2, a factor of 2.5. And the cell size went up by, what is that, a factor of 6? About. Beware exponential growth. It will get you each and every single time. But this looks more reasonable now. This could actually probably decently predict the flow around the sphere. As a matter of fact, it's probably more than what we need to predict the flow around the sphere. But you can, with a little bit of time, take a look at some of these settings, tweak them, and see what they mean. See what they do. Just sit there for 30 minutes, whatever, play around with them. Read a little bit of that documentation, look at what the settings do, and then remesh a thing to see what they do. To make sure you kind of understand where these buttons are, I will not be uploading this file, but I will be uploading this recording. So you'll be able to follow along and generate a file that looks an awful lot like this and see what these different settings do, if anything at all, right? So, that said, I think I'm going to go ahead and leave it here. I do need to get going and not too long anyways. So, hopefully this video helps people get a little bit of a crash course in what we talked about before, right? So we went through generating our block, generating our cylinder, subtracting one from the other to generate our air volume. We selected some of the physics. We talked about a little bit of the reasoning behind selecting different physics. We talked about some of the meshing, specifically with 2D meshing, some of the options that we needed to select, the badge for 2D meshing, and we generated a mesh. We also generated a region that is actually going to be simulated. So I'm not going to explain what I'm doing just yet, not now, but I'm going to set a couple of boundary conditions and briefly simulate this, and let's just see what it does for just a little bit here. So velocity inlet, we're using a velocity inlet of 15 meters per second. So that's probably all well and good. I'm just going to save this somewhere. Seems to have hung a little bit. Bear with me. There we go. Okay, this PC. Okay, I'm just going to put it here. Cylinder. Okay. Not very big. Even mesh, this is only 16 megabytes, right? Small file. No biggie. 3-dimensional files will be a different story, but this one's pretty simple. Physics values. I don't think we need to change anything here yet. Okay, that should be fine. Save, initialize, run. Aha, okay, it's running. It actually seems to be running pretty well. Again, I'm not explaining what I'm doing right now. We will get to that a little bit later. But notice this thinks it needs updating. Well, I changed some of the boundary conditions, and it does know what some of these boundaries look like, or it does know automatically that, like, hey, he told me this is a velocity inlet. A velocity inlet shouldn't have prism layers on it, so I'm going to get rid of them. The fact of the matter is, I already got rid of them. If you remember this custom control, I told it no prism layers. Oops. I told it no prism layers. But it's not thinking that far ahead. It just knows that I changed something and knows that it needed to or it thinks it needed to update because of it. So I just remeshed. I'm going to clear the solution, which is solution clear. This will throw out any numbers, but not the mesh. The mesh stays. And let's just take a look at what does pressure look like. So I created a new scene, scalar scene, and I want to select what scalar field I'd like. I could either do that here, or I can click on this. This is actually slightly newer than the version I'm used to, and mine doesn't have this options typically. Okay, we're going to look at, let's say, static pressure. Don't clip max, don't clip min, auto max, auto min. That's fine. Okay, we're going to look at static pressure. Well, gravity, so it's actually has slightly higher pressure at the bottom because air has weight. It has slightly lower pressure at the top because air has weight. But let's run. And we can see this is running so fast because there's so few cells that it's almost a video. Almost. But each one of these lines that goes by is an iteration. Every time this you can see this update, that's what we refer to as an iteration. It's running those equations, figuring out what are the pressures, what are the velocities, what are the temperatures, and updating it in real time. Or, well, as fast as it can, which is a couple of FPS in this case. It wouldn't be unusual to take minutes per iteration for more complex sims. But this simulation is absolutely running. It's a little bit annoying because it's rearranging our scalar field in real time. That's a little bit annoying. Let's set this to some static values so it stops doing that. Okay, little bit less finicky. It clearly has some turbulent shedding going on. We could look at other things, but this is a running simulation. Hopefully, by the end of the next class, you will all be competent to this level with the software. I will be posting these recordings. You will be able to watch them before class this Friday and hopefully come a little bit more up to speed. And we will proceed with talking through a whole bunch of this on Friday. Until then, I hope everyone has a interesting time with the week and looking through this recording and figuring everything else out. And like I said, we will talk about this again on Friday.